Start these lectures today, and you want to introduce yourself?
Yeah, so no, I just want to say, so this is Andrew Snowden here. Andrew will be my course assistant for this course, and so if any of the graduate students are interested, you should talk to me or to him. Okay, people are not in our group, especially. Yeah.
Okay.
All right. So it's great to be here. Yesterday in the morning, I had to shovel snow before I took my flight, so it's a nice change. That's the size I was planning to write. Is that okay? The back? Yeah? All right. Okay, so my course is going to be about periods of modular forms. You saw examples of periods earlier today. Mainly, I'm going to be interested in period relations. So let me explain what the motivating question is. Firstly, what's a period? Okay, I'm going to give a very informal definition, which will be fine for now. So let's say V is a variety over a number field F. Okay, and let's say that omega is an algebraic differential form on V. On V, that's F rational. Okay. You might just think of an elliptic curve over Q and the Néron differential in this elliptic curve, for example. Right? Let's say that I pick some embedding of F into the complex numbers, okay, sigma. So I can think of V as a complex variety. And let's say gamma is a topological cycle of the right dimension on V sigma C, so that I can make sense of the integral of omega over gamma. Okay? So that for me is going to be the typical example of a period. An algebraic differential form rational over a number field, and you integrate it over a closed topological cycle. Yes, closed. Okay, now the motivating question or the motivating problem is the following. It comes from the Tate conjecture, which was mentioned in the previous talk. And I'm going to talk about just one consequence of the Tate conjecture. Namely, if you have two varieties, say V1 and V2, both defined over the same number field, then you can, so variety for me will always mean smooth projective, right? Never, there's nothing bad ever going on. And so you have the Galois group of F bar over F acts naturally on the étale cohomology of V1 and V2. So you have Galois representations. And suppose you are in a situation where these two different spaces of Galois representations have a common irreducible Galois representation. So suppose there is a common, say, irreducible Galois representation in these two spaces. Okay, then this is fine. All right. So the Tate conjecture will then predict that there should exist a cycle on the product V1 cross V2. So it's a correspondence that realizes this isomorphism. Namely, you should have some cycle Z which sits inside V1 cross V2, such that if you pull back this piece of the cohomology on V1 to the cycle and push it forward, you should get the other back. Okay? And in Victor's lectures, he gave some examples of where you would where such a thing happens and where you expect the cycle to live. Now, the Tate conjecture is there are not many cases of this known. It's kind of very difficult. But I want to focus on one concrete consequence of the Tate conjecture. Namely that if you knew that such a correspondence existed, then this should give you relations between periods on V1 and periods on V2. This is at least easy to imagine, right? If you have an interesting cycle in the product V1 cross V2, you could transfer integrals from one variety to integrals from the other variety. Okay? So, so the question I'm going to focus on is the following. Can we prove such period relations without knowing the Tate conjecture? Okay. And you might ask, why would we be interested in proving such period relations? And so there are two main reasons, at least for me. The first is that periods occur as the transcendental parts of special values of L functions. So you know there are all these conjectures about special values. They involve periods because you have to divide by a period to make the L function algebraic. And oftentimes you'll prove something, but you have the wrong period. And then you have to establish a period relation that shows that whatever you expect to be true is true with the correct period. Okay? That's one reason that I'd be interested in this. The other reason is one might hope, so this is just hope, that this gives some ideas on constructing algebraic cycles. So maybe this is naive, but for me this is a hope that if you try to prove some of these period relations, you may get ideas on how to actually construct the underlying algebraic cycles to prove the Tate conjecture in these cases. Okay. So the specific examples that I'll be looking at will all come from Langland's functoriality. Okay. Namely, the Langland's conjectures and functoriality often predict that you have relations between automorphic forms on different groups or on different Shimura varieties. And so that's a very natural setting to study the Tate conjecture. Okay? And we'll try to see if in some of these cases we can establish the period relations directly. All right. So move this. Yeah. Right. So in fact, I'm going to focus on the very simplest case of Langland's functoriality, which is the Jacquet-Langland's correspondence. Okay. All right. So let me just recall the setup. So let's say I start with F, a classical modular form. So for simplicity, let's just say this is an S2 of gamma 0 of n. Okay. So it's a cusp form of weight 2 and gamma 0 of n for some integer n. And we'll assume that F is a new form. namely that it's an eigenform for all the Hecke operators. It doesn't occur, that system of Hecke eigenvalues doesn't occur at any level dividing n, strictly dividing n, and further I assume it's normalized. So if you wish, f is some a n q to the n with a1 equals 1. Okay. Now, what one knows is that, if you look at the field generated by all the ANs, so Q adjoin all the ANs, we'll call this field KF. This is a number field. Okay. And further, to such a form F, you can associate a Galois representation. In fact, a two-dimensional Galois representation as follows. So let lambda be any prime of Kf. Okay, and then the representation is a representation of gal q bar over q into GL2 of Kf lambda. Take the completion of Kf at lambda, and there's a two-dimensional representation. So this was initially constructed by Shimura. This construction in weight 2 was Zero Shimura, and this extended in higher weights by Deline, and weight 1, Deline and Serapin. Let's just focus on the weight 2 case. Okay. This representation is characterized by the following. By the following properties. Firstly, if I take a prime p, which doesn't divide n in lambda, or n in L, where L is the, say L is the prime below lambda, so say lambda divides L in Q. Then such a P is unramified. So call this representation rho f lambda. This implies that rho f lambda is unramified at P. And secondly, we can say precisely what the characteristic polynomial of Frobenius at P is. So the characteristic polynomial of rho f lambda of Frob P is t squared minus apt plus p, where ap is the same ap that comes up in the Fourier coefficient. So it's the pth eigenvalue. Okay, and one way, and how does Shimura construct this? Well, to construct this, he looks at the modular curve x naught of n, and then looks at the Jacobian J0 of n, and you have to look at the Tate module of the Jacobian, and that's where you construct this. From the point of view of étale homology, you can think about this construction as coming from H1 étale of x naught of n, okay, with, say, QL coefficients. Okay. I won't use anything fancy about étale homology. You should just, if you don't know what that is, that's fine also. All right. Okay, so that's one way to construct. So you have classical modular forms, you have two-dimensional Galois representations, you can construct them by looking at H1 étale of this curve, this modular curve x naught of n, right? Now it turns out that there is another way you can construct these representations, and this came up in Victor's talk. Namely, it might happen that, that you can find the same system of Hecke eigenvalues on a quaternion algebra. So I'll explain what this means. It might happen that f transfers to a quaternion algebra. So let me, in fact, an indefinite quaternion algebra. That's what I need. And in that case, we can also get this on Shimura curves. So mail. Case rho f lambda can be realized in certain Shimura curves. And I'll explain this in more detail right now. So let's say that B is a quaternion algebra over Q. So quaternion algebra is just such a, I guess if you've not seen this, but then this wouldn't make much sense, but it's a central simple algebra over Q with center Q, Q with that is 4-dimensional. That's a Q vector space. So such a thing would be given by a set of equations of the form x squared equals a, y squared equals b, xy equals minus xy, where a and b are rational numbers, and sorry, xy equals minus yx. That was bad. Okay, and a and b would determine the state, right? Okay, now what is true is that if you take how a quaternion algebra is determined, they're determined completely by what they do locally. So locally, there are two possibilities. If you take B tensor QV, you might either get the matrix algebra M2 of QV, or you might get the unique up to isomorphism quaternion division algebra over Q. Over QV. So for every completion of Q, there's a unique division, quaternion division algebra over QV, and when you tensor this global algebra with QV and look at it locally, you might get either the matrix algebra or you might get the unique one. And what is true is that this happens for all but finitely many V. And this will happen exactly at a finite set of V. And by class field theory, one knows that this finite set has to be even. Okay. Conversely, if you're given any finite set of primes, you can construct a unique up to isomorphism quaternion algebra over Q that gives you a division algebra, that finite set of primes, and that is split at the other primes. Okay? So I'll use the word, in this case, I'll say this is split. This is the split case. Okay, and this is the ramified case. Right? Okay, so let's say that we had a quaternion algebra over Q, which is indefinite. So suppose B is indefinite. What this means is, when you tensor B with R, then you don't get the Hamilton quaternions, but instead you get the matrix algebra, M2 of R. Okay? All right, and now let's take an order, so that O be an order in B. So an order is just a subring of B that is rank 4 as a Z module. I'll give an example in a second. Okay? So, for example, B could be the matrix algebra, okay? And O could be the following order. O could be the order M2 of Z. That's an order. Okay, that's one example. Or you could take this integer n that we had before, and you could take O to be the set of elements A, B, C, D in M2 of Z with the property that C is congruent to 0 mod n. Okay. So these are examples in M2 of Q, but likewise you can write down examples of orders in any quaternion algebra. And now you can take let gamma be the units in O, so the set of reduced norm 1. So I should have said this, but any quaternion algebra comes equipped with a reduced norm and a reduced trace. Okay. So in fact, there's an involution called the main involution. It's called the main involution. and the norm is just, as you might imagine, the product xi, while the trace is the sum. Okay? If you've never seen this before, you might think of what the main involution should be for M2 of Q. All right. So let's take gamma to be the set of all x in O whose reduced norm is 1. Okay? And let's fix this isomorphism of B with B tensor R with M2 of R. So if you fix this isomorphism, let's call it I, then I can think of gamma sitting inside B tensor R, right, which is M2 of R. But the fact that I've started with elements of reduced norm 1 means that gamma in fact lands inside SL2R. Okay? So this gives me examples of subgroups of SL2R that you wouldn't get from by looking at, say, gamma naught of n. Gamma naught of n is this subgroup. Oh, can't see this? Oh, okay. All right. Okay, so let's go to page 4. Okay. All right, and now you can do all the same things that you did with gamma naught of n. Namely, you have an action of SL2R on the upper half plane. So you can take the quotient. It turns out this is a discrete subgroup. So gamma is discrete. SL2R. So you can take this quotient H mod gamma, the upper half plane mod gamma. This is the analog of the curve. So if, for example, that the order was the order we saw here, right? Maybe I should have called that something else, but let's just, if you had that order, so I'll call it O sub n, say. So example, if you take O sub n, then gamma is just gamma naught of n. And then the curve that you're getting here is just the analog of y naught of n. Okay? Which you can complete by adding these extra cusps to make that x naught of n. But the good thing, or I don't know, but the interesting thing is that if your quaternion algebra is not the split algebra, M2 of Q, then this H mod gamma is already compact. Okay? So there aren't any cusps. Now you might think this makes life easy, right? Because there aren't any cusps, you don't have to compactify this. But in fact, it makes life quite hard to do arithmetic, because one of the key tools for the usual modular forms is the Q expansion principle. The fact that you can make Q expansions and that they have very good arithmetic properties. Right? And this tool is completely unavailable when you want to study modular forms with respect to gamma. Right? So just say you can define modular forms in the usual way. Hecke operators, all this stuff can be done. But Q expansions aren't available. And this makes the study of modular forms on such gamma somewhat difficult from an arithmetic point of view. Okay? All right. Now, I didn't say, well, what do we know about this H mod gamma? You know it's a complex curve, right? So I'm going to call this XB. You know this is a complex curve. But Shimura showed that, in fact, X sub B has a canonical model over Q. And this model is characterized in the following way. As follows. You look at embeddings of imaginary quadratic fields, so that K be imaginary quadratic, and you take embeddings of K in B. Okay? So look at imaginary quadratic fields that embed in B. Okay? You can easily work out which ones they are. right? So if K embeds in B, then K cross, so remember that B tensor R is M2 of R, right? So you can compose this embedding of K and B with this isomorphism, I, and that will send K cross into GL2R, in fact into GL2R plus. Okay? And it's easy to see that there's a unique fixed point of the action of K cross. So K cross therefore acts on the upper half plane, and this action has a unique fixed point. Which I'll call tau, right? So I can start with this tau, which is an H, and look at the image of tau in H mod gamma. Okay. That gives you some point. And Shimura's characterization is the following. You require that this point, which I'll call say p tau, that p tau be algebraic, and further that the Galois group of Q bar, in fact over Q, or in fact Q bar over K, I'll just represent, should act on such points in a prescribed way. This action has the whole theory of complex multiplication written into it. Okay, so all I want to say is that there is a canonical model defined over Q, and Shimura showed that such a thing exists, and it's characterized by this property. Okay, so this is. Is that okay? All right. So now. Okay. Right. So I'm just going to use x sub b. I'm not going to be very precise, right? So x sub b will just be one of the curves that we get in this way, right? And you can think about modular forms on gamma. So modular forms. So let's say I pick a modular form G, which is of weight 2, right? And again, there's a theory of Hecke operators. There's a theory of eigenforms and so on. So let's pick something that's an eigenform. Say G is an eigenform for the Hecke algebra. Okay. The Hecke operators are indexed by the primes and so on. Okay. The situation is very much like GL2. So you might ask yourself, okay, do I get new systems of eigenvalues? New systems of Hecke eigenvalues in this way. Okay. And the answer, which goes back to Eichler and completed by Jacquet and Langlands, is that no. In fact, all systems of Hecke eigenvalues already appear on M2 of Q. Okay, so you don't get any new systems of Hecke eigenvalues. So you might say, why should we even look at these forms since you don't get them? One reason came up in Victor's talk, right? Namely, if you want to construct rational points, then you're often interested in looking at the curves associated with these other quaternion algebras, and you can make constructions in their situations where the usual Heegner points don't work, but you use Heegner points coming from the Shimura curves, and they work. Right? That's one reason, but there are of course many others. All right. So Eichler and Jacquet-Langlands showed that in fact all systems of Hecke eigenvalues already appear on M2 of Q, and Jacquet-Langlands in fact give a criterion, and I'll talk about this later in the talk, for a system of Hecke eigenvalues on M2 of Q to appear on a quaternion algebra. And I'll get to this towards the end of the talk. All right. Now, but of course, we could do the following. We could just start with such a G, and we know that, so we have G on XB, right? And X sub B is defined over Q, and exactly the same construction will give me a Galois representation, rho G lambda, from the Galois group of Q bar over Q to GL2 of KG lambda, where KG is the field generated by the Hecke eigenvalues of G. But remember that such a G comes from an F, or corresponds to an F on X. I'm going to call this X M2 of Q. Okay? And we had a rho F lambda over there. Right? Now, F and G have the same system of Hecke eigenvalues, so Kg equals Kf, and these Galois representations are characterized by the property that the trace of Frobenius, or the characteristic polynomial of Frobenius, is given in terms of the Hecke eigenvalues. So these two representations are isomorphic. Okay? Now, one of them starts life on H1 of et al. Of xb, and the other one is an H1 of the modular curve x, or xm2 of q. Right? And here you have an example where the Tate conjecture should come into play. You have the same Galois representation, and it occurs on two different curves. Okay? So the Tate conjecture will predict that in fact there is a cycle on the product xb cross xm2q that realizes this. Happily, this is one case of the Tate conjecture we know when this is due to faultings. So at the same time that faultings proved the Mordell conjecture, in the same paper, he showed that the Tate conjecture is, that this case of the Tate conjecture is true. Okay? For H1s of abelian varieties and so on. So faultings implies this is okay. Okay. So in this particular case, we know how to construct this cycle. However, I should point out three things. The first is there is no canonical construction of this cycle. There's no known canonical construction. No, it's not going to be, because it's only unique up to homological equivalence, firstly, right? So it's not going to be unique. And that's one problem, because you expect a cycle in the Chow group mod homological equivalence, because that's all this thing sees. And it's just not clear how you would ever construct something like this, say in a moduli theoretic way, because it's not clear how to do this, right? So, okay. So there's no known canonical construction. Secondly, you might say, all right, we've done the case of weight 2. What happens with higher weight? So what if the weight of f is bigger than 2, right? In that case, you can construct motives. So Scholl has constructed motives associated with these modular forms. And you might ask for an isomorphism in some category of motives, and this we don't know how to do. Okay? And third case, which is the one I would kind of want to focus on for the rest of this talk, is, well, let's look at Hilbert modular forms. So let's replace Q by a totally real field. Field F, so you get Hilbert modular forms. And what can one say about the corresponding statement there? Okay? And that's what I'm going to talk about for the rest of this talk, at least. Okay, any questions so far?
Sure.
Yeah.
So you said that the Schimura is associated to order O is defined over Q.
Yes.
Is this always true, or is that financial right?
No, I said the Shimura. So I want to think of the whole Shimura variety associated to B, okay, and that's defined over Q. So you think of it as an infinite system of. Right. For example, yeah. Well, I don't want to, x1 of n is a bad thing, but it has very many components, and you want to look at the whole thing, and that's defined over Q. x0 of n is connected. So, okay. So I'm going to talk about Hilbert modular forms. So let's say F is a totally real field. I'm not going to define precisely for you what Hilbert modular forms are, and you won't need to know that just to follow the rest of this talk. Okay? So the point is that instead of M2 of Q, so just as an example, so what does it mean for a field to be totally real? By the way, it's just that every Archimedean place of this is real. Okay? So for example, you may think of F to be Q square root D, where D is positive, right? That's a real quadratic field. Or you could take F to be Q zeta M plus zeta M inverse, where zeta M is the primitive M through infinity. And that's a totally real field as well. Okay? All right. So over totally real fields, you can define the notion of Hilbert modular forms. And these you should think of as being associated to the matrix algebra M2 of F. Okay? And if F has degree over QD, then there's not just one weight at infinity, but there's a bunch of weights, one for every Archimedean place. So let's say that so I'm going to call sigma F infinity the set of infinite places of F. Okay? And so there's going to be a bunch of weights. So let's say that in general there's going to be a bunch of weights K1 through KD. The weights. Okay? And let's just restrict, as we've been doing, to the case of parallel weight 2. Okay. So let's just assume that all the weights are 2. All right. Now, just as in the case of Q, instead of looking at the matrix algebra M2 of F, you could take a quaternion algebra B over F. And you could define the analogous notion of quaternionic modular forms or quaternionic Shimura varieties. So X sub B will be a Shimura variety associated to B. It's not important for you to know exactly what this is, except you should know what its dimension is. Okay? So I'm going to tell you what the dimension of this thing is. The point is that if I take B tensor R, now in the previous case I only looked at the indefinite case, but now in this case, well, B tensor R, there's D infinite places. So at some of them, this quaternion algebra could be ramified, and at some of them it could be split. Okay? So let's say that B tensor R is the product of n copies of M2 of R, and then D minus n copies of the Hamilton quaternions. Sorry? Tensoring over Q. Yeah. So, right? Now, this variety X sub B, so it turns out that X sub B, does somebody want to guess what the dimension is going to be? Somebody who hasn't seen this before? Okay, it should come from this part, right? M2 of R, because that's the part that you can make that act on a bunch of copies of the upper half plane. So X sub B has dimension n, exactly n, right? Where is it defined over? Okay, so it's defined. It turns out that it's defined. So previously, when we worked over Q, our varieties were all defined over Q. But in this case, it will turn out that it's defined over a specific field called a reflex field, which I'll call F sub B. Okay, so I'll tell you quickly what this is. So I'm going to think of my F as embedded in Q bar. Okay, and I'll also pick some embedding of Q bar in C, right? So I can identify all the embeddings of F, so hom F Q bar will be identified with the set of places with sigma F infinity. Okay. All right. And what is this reflex field going to be? Well, it'll live inside the Galois closure. So let F gal denote the Galois closure of F. Right. And the reflex field is something that's going to sit inside there. Okay. So I have to tell you what the Galois group of Q bar over FB is. Okay. And this is going to be exactly all sigmas in the Galois group of Q bar over Q, such that sigma fixes, so there's a set of places here, right? So let's say that tau 1 through tau n are the places where B is split. Okay? Then what you want is that sigma composed with the tau 1 through tau n gives you tau 1 through tau n in some different order possibly. Okay? So it doesn't fix them pointwise, but it fixes this as a set. And so look at this subgroup of the Galois group of Q bar over Q and take the fixed field. And it's obvious that it's contained inside the Galois closure. So there's some other field that this is going to be defined over. So for example, I fixed one embedding. So let's say my places here are V1 through, so if sigma f infinity, so where's that? Let's say this is V1 through Vn, Vd, where V1 is the place given by the chosen embedding of over here. Then I'm going to get in this way, for example, so if B is split at V1 and ramified at V2 through Vd, then in fact this field is just FB is just F. So then FB equals F. If B were split at some Vi and then ramified at all Vj which are not Vi, then Fp would exactly be sigma I F, where sigma I is the embedding of F and Q bar that corresponds to this place, which I've called Vi. Okay. This is no. These are not necessarily fields. So these are not PEL type Shimura varieties in general. So it's not. I think so, but I'm not. Yeah, this is what comes out of the theory of canonical models. This is where the canonical model is defined over it. But I'm not sure of the exact answer here. All right, so. Right. Now it turns out that there is you should expect that associated to this. So let's say I have a modular form F. So suppose F is a Hilbert modular new form. Then you should expect that associated to F is a Galois representation with a Galois group of Q bar over F into again GL2 of some field F lambda. And you might wonder, how can we construct such a Galois representation? So I'll call this rho of lambda. Okay. Now, if you were in this situation, if you did have such a B which is split at V1 and ramified at all the others, right? So I'll say example, we'll call this example 1. So, yes. Well, it's just given by the Hecke eigenvalues. Yeah. So if you had a quaternion algebra, B as an example 1, right? Then X sub B is defined over F, right? And it has dimension 1. So you're very much in it's like the situation over Q, and you can look at again H1 of X sub B. Okay? And you can construct a Galois representation there, and that's how you can construct this two-dimensional Galois representation. Okay? If you had such a B. Such a B might not exist, and I'll come back to this point later. Now what happens if you take a more general B? If you take a more general B, then X sub B is only defined over this reflex field F sub B, right? It turns out that there is a natural representation you can look at in the middle dimensional cohomology, but this natural representation in the middle dimensional cohomology has dimension not 2, but dimension 2 to the n. And in fact, it can be constructed, so this can be constructed from rho f lambda by a process called tensor induction. Okay. Which I was going to explain, but I probably don't have time to. But at least over, so if you take this natural representation that you get, I'll call it, say, rho sub b, this is on xb. If you restrict this to the Galois group of q bar over the Galois closure, then it turns out that this is just isomorphic to the tensor product of what? So let me just say, so this is the tensor product over, so B, remember, is, so where is that? Right, so B is split at a bunch of Archimedean places, tau 1 through tau n, right? So this is going to be, I'm going to call this rho tau 1, rho tau n, right? Where rho tau I would be constructed from, let's say, a B tau I, which is split at tau I and ramified elsewhere. Okay. So you can make a two-dimensional representation by picking a quaternion algebra that's split at one place and ramified elsewhere. But if you take a quaternion algebra that's split at a bunch of places, then the natural representation you get is 2 to the n dimensional, and it's like a tensor product of a bunch of these two-dimensional representations, where rho sub tau I is just your rho, but it's twisted by, it's conjugated by tau I, okay? Because it's defined over the field, it's defined naturally over tau I of f. So you see that this representation is this is on x sub b, and this is on a product of curves x tau 1 cross x tau n. Okay? So again, you're in the situation of where the Tate conjecture should apply. Okay? Now I'm going to use a new piece of paper because I want to show something. Okay, So the Tate conjecture says that there should be a cycle on this product that realizes this isomorphism at the level of Galois homology. All right. There's a weaker statement that you could make, which is the following. Suppose, so that I'll call 1. So 2. Suppose B and B prime have complementary ramification at infinity. So if I take the set of infinite places where they're ramified, let's say they're complementary, okay? Then what you should have is there should be a cycle on x sub b cross x sub b prime cross x m2f, right? Okay. And thirdly, this is even weaker. Suppose b and b prime have the same ramification at infinity. Then there should be a cycle on just x sub b cross x sub b prime that realizes the fact that the two representations that you get there are isomorphic. All right. So let me just say, how much time do I have, David? When did we start? 5 minutes? Okay. All right. So right. So these are consequences of the Tate conjecture. These are examples where we expect the Tate conjecture to hold, and we don't know how to prove this. Okay. But I want to talk about Shimura's conjecture, which is a concrete conjecture about periods that will follow from this. Okay. And the idea is that if you take the form f sub b, and I'm going to talk about how to normalize this in a bit. You can take the Peterson inner products, the Peterson inner product of f sub b with itself, and the question is, how are these related? as B varies. Okay. And each of these three statements will give you a concrete prediction for how the Peterson inner products are related when you normalize the forms correctly. Okay. So, for example, here what you would get is f sub b is equal up to, say, q bar cross f sub b prime, f sub b prime. And here you would get f sub b times f sub b prime equals ff up to q bar cross, where f is the GL2 form. And there's going to be a corresponding statement there that I'll talk about more precisely next time. I think there's no point in rushing it. So next time what I'll do is I'll start off by formulating this conjecture, right? Which is a conjecture on periods that would follow from these, that would follow from the Tate conjecture if we knew this, but it turns out we can actually prove this conjecture on periods independently. Okay? So it turns out that the corresponding algebraicity statements, so Shimura in fact conjectured the corresponding statement in this case. So this is Shimura's conjecture, and he showed both of these cases. Okay? And Michael Harris settled that the case 1 under the condition that there are such BIs. Okay? That there is that for each I there's a quaternion algebra which is ramified, which is split at that place and ramified everywhere else to which this form transfers. Okay. I'm going to explain how one can in fact remove that condition. That's one thing that I'll explain. And the second thing I'll explain is I want to talk about an integral version of this conjecture. So this is a conjecture that works up to algebraic numbers, but can you say something p units? Okay. And that's going to be the main focus of the rest of the talk. Questions? Do you have questions? No.